Okay, so let me continue to study on beam. Beams are really important structure. So most important structure, I think, is a beam. So straight beam. So what's the difference between beams and bar? Bar is have a loading, actual loading, right? But beam is subjected to the transpose loading. So difference is this. This is a loading for bar, right? This is loading for beam. So this is a big difference. So because of different pattern of loading, the behavior to bear the external load is totally different. Okay, so the assumption was a plane cross-section, originally normal to the midline of beam, remain plane and undistorted. You remember? Okay, that assumption is a very important assumption for kinematics of beam. Okay, so now let me consider a beam. This is beam, okay, and let's say this is a y-axis, and this is x-axis, and this beam have some transpose loading, which is distributed, okay, something like that. And let's consider some point x from the origin, and let's consider small part of the beam, its length is very small, delta x. So I like to consider only this part. And this beam can have some cross-section y and x, g. Okay, this is cross-section of beam. Now I like to consider the prismatic beam. Prismatic beam have a constant cross-section along the beam length. And let's consider over there the shaded part of the beam, delta x. Okay, so let's consider the applied the distributed loading have a y direction. Okay, sorry. Okay, so now let me draw the free-body diagram. What kind of forces can act on this part of the beam? So first of all, it has some distributed force here, Qx. Because the delta t is very small, Qx can be considered constant, right? Because in this case, length is very small. And this beam can meet some shear force and moment. Let's say shear force moment in left side of this beam, and right hand side shear force will be changed a little bit, V plus delta V. Okay, and moment will be changed, M plus delta M. You know the M and B is a resultant force, which is calculated from the integration of stress on the cross section. Okay, now let me sum all the poles in y direction. It should be 0, right? So let's sum all the poles. So minus V plus V plus delta V and plus Q and delta X. This should be 0, right? Okay, then here this V and this V become 0, and in this equation we can find dx dv plus q equal 0. This is the first equilibrium equation for beam. So this equation gives us relation between shear force and transversely distributed load. Okay? So now let's also consider moment about O. Here let's consider this is a point O. So for this point O, if I sum all the moment, it should be 0, right? Okay, so I like to define this direction of moment is plus. Okay, then M, okay, minus M plus delta M, and also we have a moment. So this is a point I am considering to calculate moment. So this force cannot make any moment because of the moment time is 0. But this force can make a moment, right? So plus the moment arm is delta x v plus delta v, okay? And also distributed load make a moment, contribution to the moment, plus moment arm equal 2 delta x over 2. So this is a constant almost, right? So center of this load is here. Okay, center of this distributed load is here. So this is half of the dx. So 2 delta x and magnitude q delta x is 0. Okay, then m. And that equation, here, let's look at the minus delta m, right? And delta x v plus delta v. And here, we have a scale of delta x. Delta x is very small. So scale of delta x is much small, right? So we can delete this part. And also here, delta x is very small and delta v is very small. So if I multiply both small value, then this is small. So we can get rid of this. And finally, we are going to have one more equation that is okay, so Okay, minus. Okay, maybe something wrong I calculate here. Plus. Sorry. Here so I need to make this sign. Okay, sign was changed. So you need, please can you change the sign of moment? So then here plus minus. Okay. So then dx dm plus v equal 0. This is a second equation. So we can choose the direction of moment, but it depends on the sign convention. What kind of sign convention I have. So here I wanted to use sign convention for this type of moment. Is give us a positive moment. So if I give this type of moment, we can result in this equation. So in this two simple beam problem, we have two equilibrium equation. One is about the shear force and distributed load. The other is the give us relation between moment and shear force. Okay? Both are local equilibrium equation for beam. So one equation dx dB plus qx equal 0. The other dx dm plus v equal 0. So we can combine both. So we can put this into here. Okay. Then we can have second order ordinary differential equation m minus q x equal 0. So this third equation gives us relation between moment and distributed force. So when we solve the beam problem, we need to consider all of these equilibrium equations. So equilibrium equation, it's about force, right? Force and stresses. But to make a complete beam theory, we need to also consider strain and displacement, right? So now let me talk about kinematics. So first beam theory is Euler beam theory. Euler Bernoulli beam. So this is a very classical beam theory. Actually, there are two very famous beam theory, and both are very classic. One is Euler-Bernoulli beam theory. The other is that Timoshenko beam theory. Okay, so when you are undergraduate students, so you only meet this Euler beam theory. But in my class, I like to also teach about Timoshenko beam theory. Timoshenko beam theory is a little bit more complicated. So for Euler beam theory, it has an assumption for kinematics. Actually, this is an additional assumption. So additional assumption. So plane cross section originally normal to the midline of the beam remain normal to the midline during deformation. This is the Timoshenko beam theory. So here key point is this one. Remain normal to the midline during deformation. So do you remember the kinematic assumption for beam? I mentioned before, and this new assumption is a little bit different. So this means, let's say we have a beam here, straight beam, and we have some reference line along the beam. This is we can say midline. It can be any line, okay? And let's cut the some surface A and B originally normal to the midline, okay? And let's consider some deformation like this, okay? And this is a midline. So this is a bending deformation, right? So in previous assumption, the original line surface, okay, made by A and B is it should be plane, right? Something, I mean straight line here, right? That was the assumption. But in Euler beam theory, assumption is like this: A, B. This new line should be normal to midline. So it can have the original assumption gave us the deformed surface doesn't need to be normal to the midline. But Euler-Bernoulli beam theory have assumption. This is during the deformation. So in deformed situation, the cross-section should be always normal to the midline. Okay? This is understand? So okay, this is original configuration. This is a deformed configuration. So this is assumption for Euler beam theory. Euler-Bernoulli beam. Okay. Now we understand the beam theory, the assumption, and now let me drive the kinematics, equation for kinetics. Let's consider beam. Okay, and this have a midline, something like that. X-axis U. Okay. Let's think this is a neutral axis. Neutral axis. And axis. What's the neutral axis? You remember neutral axis? EU. EU is right, so and EU. Axis. So in beam theory, when we make a reference line, okay, we always use neutral axis. So let's consider this bending deformation. So bending deformation. Okay, so how about here? This fiber is stretched. This fiber is compressed, right? Tension compressed. So length of fiber increase, length of fiber decrease. So compare with the original length of fiber, right? But at the neutral axis, there is no length change. Okay? So we define the neutral axis. The line where the longitudinal length change doesn't occur. So doesn't happen. So let's consider the reference line with the neutral axis. Okay, and then consider some deformation of beam. Let's say this is a deformed configuration, and let's consider some point here, some cross section here. Okay. And this point will move to this point during the deformation. Right? This is a transverse displacement B. And this line will be rotated like this. This is normal to the direction. And this rotation is theta. Okay. And actually, that theta calculate from the V, that is Vx, dx, dv, right? Because this is theta 2, same. You can think this neutral axis of deformed beam is some function. Have a function v, and slope can be calculated by differentiation about x, right? You know so here function f, x, let's say this function, we can calculate slope, 1 theta by simple differentiation, right? Right? And this theta, change of the angle in the neutral axis is same to the change of angle in the cross-sectional plane, because that assumption, both between the cross-section and neutral axis have a 90 degree, right? Okay. Then let's calculate the displacement in x direction at some position y here, y. Let's calculate the displacement in this point. So displacement y is here. So actually, because of the y rotation, this red point go back, right? Go to the minus x direction. From this point to left. So here, u equal minus y theta. So amount of this is y theta. How about the v? V is just v. So in the beam theory, the displacement in y direction is all the same at the same cross section, but displacement of in x direction is a function of rotation angle theta. Okay? So, okay, again, u equal minus y theta equal minus y dx dv, right? Then you can calculate the strain. Strain xx. Strain xx, the Young's modulus, dx du equal minus y dx v, right? From the strain displacement relation, we can simply calculate the normal strain, right? Normal strain have a distribution. It depending on the y. Okay. How about the shear strain? So transpose shear strain here. During the deformation, transpose shear strain. Transpose shear strain physically mean the angle change, right? So here we can have a, let's look at here. So originally here we have a small cube here, small rectangle here, and this is after deformation. Angle doesn't change between this fiber and this fiber. At any point, angle doesn't change. So at any position, there is no angle change. It means there is no shear strain during the bending. So we are saying this kind of bending is a pure bending. Okay? In pure bending deformation, there doesn't exist shear. So we are saying it's a transverse shear. So transverse shear strain is 0. So we need to consider only normal strain. Also, stress X, stress can be calculated by material law. E strain XX equal minus EY d square V, right? So in beam theory, stress XX is 0, is not, other stress are 0. Stress XX is non-zero, and other stress component equal 0. So other stress mean in this case stress YY, stress XY equal 0. Also corresponding strains are 0 too. So strain XX, strain XY, Y is also 0. So in beam problem, because we only consider normal stress and strain, okay, with the help of assumption, right? Problem become much simpler than, okay, solid mechanics problem, general solid mechanics problem. In general solid mechanics problem, to solve this beam problem, we need to consider 6 stress, 6 strain, right? But here we only consider 1 strain, 1 stress, right? Okay, so let's just consider one part here. And, okay, so let's consider this bending deformation. So when we calculate the moment equilibrium equation, we gave us this moment, right? Moment M. So this is a positive moment. You remember when we defined the stress, this was a positive stress, right? And this was a negative stress, right? Similarly, we can define the sign of a bending moment. So, you know, cross-sectional bending moment comes from where? Integration of stress on the cross-section. So, bending moment is the same thing, okay, to the stress. So, we need to define the sign also. So, at some part of beam and both sides, we have this kind of bending. We can define this is a positive moment. Okay? And the other direction, negative bending. Okay, so in this case, so deformation looks like this, right? So at this side, strain distribution and stress distribution will be like that. Okay, strain distribution or stress distribution. So here at the top, compressed, bottom tensioned, right? So if I integrate this shape of stress, we can calculate moment, right? So moment can be calculated. M equal stress XX Y dA and cross section A, right? This is a reduction formula. You remember? But because we said this type of moment, the internal moment is a positive moment, we need to put the sign minus here. Then we can have a positive moment. Okay, so then moment is calculated by applying this equation into here. A E y squared B. Here y equals dA. Okay. Understand? So moment can be calculated from the transpose displacement, and that equation become E y squared A dA, okay, dx dVB. Here, this is the only change. This is constant. This value is constant on the cross section, right? Because we have a same vertical displacement on the cross section for a specific position x. So this equation can be changed like that. Watch this. Huh? This is a second moment of inertia, I. Then E I dx squared dV. I equal second moment of area about g-axis. So g-axis is this axis. Okay, this is g-axis. So now I introduced a little bit new concept, I. So I know all of you very familiar with I. So finally, m equal ei dx v, right? That's the final equation. So, where this equation comes from? So, to drive that equation, we used, first we assume kinematic field, displacement, right? This was the assumption from Euler-Bernoulli, right? And from this assumed displacement field, we calculate strain, and then we use the material law. So we can calculate stress, then we integrate that stress on the cross section and find the moment. So to find this result, we use the material law, strain displacement relation, right? Right? So the next thing is that you remember local equilibrium equation? Local equilibrium equation. Local equilibrium equation was dx dm minus q equals 0. We can put this result here. So then dx dei minus q equals 0. This is carbon equation for beam. So when we solve the beam problem, we need to use this equation. Okay, this is a fourth order ordinary differential equation, right? This equation gives us relationship between external load Q and displacement V, right? And to drive this equation, we use local equilibrium equation, material law, and displacement strain relationship. So we used all the basic solid mechanics, the carbon equation, right? Okay, and now we need to also, to solve that equation, we need to have a boundary condition, right? So that's the force of the ordinary differential equation. So to solve that, we need to integrate 4 times, right? So how many intelligent constants you can have? 4, right? Then at least we need to have a 4 boundary condition. 4 boundary condition. So with boundary conditions, so one is about displacement, V, and the other one is just rotation. Rotation is also displacement, rotation, and shear force. and m is a moment. So we have a forward. First two is a displacement boundary condition. Last two is a force boundary condition. Okay. So when we apply the force shear force boundary condition, we can use this relation B equal minus EI V and M equal EI B, right? So I drive this equation over there, and also V can be the relation between shear force and moment, right? If I differentiate moment, we can have a shear force, right? After multiplying minus 1. This is simple. Now it's very, very important to define sign convention. So moment is plus, this is a plus moment, and shear, this is shear, this is a plus distributed load plus. This is sign convention. Because when we drive this carbon equation, we use this sign, right? When we drive the, local equilibrium equation, I give this type of moment and this shear force, and that distributed load is a plus. So when we drive, if we change the carbon equation, it becomes change. So we need to use the consistent sign convention. So when some sign convention is defined, we need to use the proper carbon equation. So okay. And also one of very important equation is that relation between moment and stress. So stress xx equal minus EY dx square V, and M equal EI dx V. This is already I gave you before, and from this, because this one and this is the same, from both equations we can derive stress xx equal minus I m y. So from the cross-sectional moment, we can calculate all the stress on the cross-section. Okay, so any question? This is a beam theory, but this beam theory is, you already know this beam theory, right? This is exactly same beam theory you learned in your undergraduate school, some material mechanics class more or some simple mechanical, but derivation would be a little bit different, right? Because now we know all the fundamentals about solid mechanics. So my derivation is related with the solid mechanics carbon equation. But in undergraduate school, you don't know about the solid mechanics, right? So you can have a little bit different derivation. Okay, so now it's time to solve some example problem. Example, y-axis, x-axis, I have a straight beam, and actually this is a simply supported. So we have a hinge and roller at both sides, and transpose load is distributed on minus y direction. So qx equal minus q0. And this is a prismatic beam of length L. Prismatic beam with I, constant I, and also Young's modulus E is constant. So in beam, EI is named bending rigidity. Okay, EI is bending rigidity. So if the EI value is big, beam is steeper. So harder to bend the beam, right? Okay, so first of all, we need to specify the carbon equation. So carbon equation. First, post of the carbon equation. Here, because the E and I is constant, doesn't change. That equation changes a little bit. So becomes simpler, dx x minus q equals 0. If the E or I is not constant, we cannot use this equation. We need to use this equation, right? And boundary condition. Boundary condition. First, displacement boundary. V 0 equals 0. Here x equals 0. At this point, we have a hinge support. So y displacement is not allowed, fixed. And also at this point, y displacement is 0. So V L equals 0. This is a displacement boundary condition and force boundary condition. Force Fourth boundary condition. Let's consider at this point moment. Moment is 0. Moment is not applied, right? Actually, because this is not, the rotation is allowed. So moment is 0. 0 equal 0. And similarly, m and x equal L is 0. So we can have a 4 boundary condition. Okay, so if I integrate this equation 4 times, here it's not xb, b, 4 times, b will be minus 24 ei q plus C1x, C2, C3x plus C4. So we have a 4 integration constant. Then applying that boundary condition, we can find solution. So applying that boundary condition, displacement will be minus q0 24 ei x. This is the final equation. So you need to solve by yourself. This is not a difficult problem. And from this solution, also we can find moment ei b equal minus q0 2 q0 x square minus lx. This is moment. And shear force. Q0. This is shear force. So when we design the beam, moment is very important, right? So this moment should be smaller than maximum moment or ultimate some moment required. So here let's plot this shear force. So here x equals 0, x equals L. X equals 0, x equals L. Okay, so at x equals 0, the value of shear force is a minus Q0L over 2, right? And X equal L here plus Q0L2. And this is a linear variation. So this is a shear force. So at the center of that simple beam problem, there is no shear force. At each end, okay, we can have a maximum shear force. So how about the moment? So we are saying this is a SFD, shear force diagram. Okay, shear force diagram. And also we can have a bending moment over there. So it looks like this. And at the center, maximum bending, Q0 L square 8. We are saying this is a BMD, MD. Bending moment diagram. Bending moment diagram. So this bending moment diagram and shear force diagram is very important to design beam. Actually, we know the relation between shear force and bending moment. This was a relation from the equilibrium equation dm plus b equals 0. You remember this equation? So m equal minus integration b, right? This is relation. So moment calculate from the integration or bending. So, and we need to put minus. So if I integrate this line, we will have here we start from here and minus, and we will have this kind of equation, right? Then if I multiply minus 1, we can have a bending moment diagram. So we can calculate the bending moment diagram directly from the integration of shear force diagram, right? Also, we know the relation between shear force and distributed load. What's the relation between shear force and distributed load? So the relation between shear force and distributed load is that dx dv plus q equals 0, right? So q equal minus v. V equal minus q. V equal minus q dx. So we can calculate the shear force diagram from shear force, the distributed load. So in this case, all the load is minus q is applied, and we can calculate the reaction at both sides. Okay, you know how to calculate the reaction, right? You remember? If I take the moment about this, we can calculate the reaction here. Also, this reaction plus this reaction should be same to the whole value of the force in y direction. So here reaction will be y direction. So 2q0l. Here 2q0l. So from here we can calculate the shear force. So at this point, this is a shear force. So if I integrate the shear force, this point go up, amount is this value, and because of this, and this is a shear force diagram, okay, and I need to invert because we have a minus value here. Then we can have this solution. So first we calculate all the reaction, then we can calculate shear force diagram. Then from the shear force diagram we can calculate bending moment diagram. So without solving this governing equation, we can also find the shear force and bending moment diagram. But it's possible for only simple system. Okay, so this is finished lecture today, and in the next class I'm going to teach about Timoshenko beam theory.